Should I wait until 9:05, Nikhil? Should we wait like a minute? You said 9:05.
No, we can start now and 3-4 minutes.
Okay, sounds good. Yeah, thanks everyone for coming to this talk. If you all have questions at any point of time, you should feel free to stop me and ask them. So this is the first talk in a two-part sequence with Alon, who's going to give the second talk, which is going to be about expanders with a little bit of a group-based focus. Okay, so I guess before I give any definitions, maybe when I say expander, you should sort of have the picture on the left in mind, like a bunch of vertices, and they're very well connected among each other. And notably, not the picture on the right, where there's a very easy way to chop the graph up into 3 pieces. So slightly more formally, the combinatorial properties that we might want in an expander are things like it's well connected, that is, any way to partition it will actually give me a lot of edges. Also, if I start a random walk at any single vertex, it very quickly converges to the uniform distribution. And also in general, it has other pseudorandom properties, like it behaves like a random graph. But OK, let's try to make this notion a little bit more quantitative. And let's define the notion of spectral expansion. OK, so let's say G is a graph. And in this lecture, we're going to assume that it's a deregular graph. But a lot of the theory smoothly generalizes even if the graph isn't regular. And the specific object of interest for us is going to be the random walk matrix of the graph. So you can think of it as taking the adjacency matrix and dividing it by D. But in general, you should think of the ij entry of that matrix PG as being the probability that if you take a random step from I, you land on J. OK, so this is like an n by n matrix. It's symmetric. So it's going to have n real eigenvalues. And you can actually show that all the eigenvalues live between -1 and 1. OK, so now the expansion is controlled by the second eigenvalue. I guess in today's exercise sheet, the first exercise is like various things you can conclude from the second eigenvalue being bounded away from 1. So to emphasize, the further away the second eigenvalue is from 1, the better expanding the graph is. And the terminology that we're going to use is that a graph is a gamma expander if the second largest eigenvalue is bounded away from 1 by this parameter gamma. Actually, I want to make a little change here. And I instead want to work with this other matrix called the Laplacian. So it's basically the same thing as the transition matrix, except I took identity and I subtracted out the transition matrix. And the effect this has is it changes the eigenvalues from being between -1, 1 to being between 0 and 2. And you're always going to have an eigenvalue at 0 corresponding to the all ones vector. And now the quality of expansion is measured by the smallest non-zero eigenvalue. OK, so the thing that's nice about this is that it actually gives a way to write expansion as some sort of algebraic inequality, which is sort of hinting at like certain proof techniques we're going to see later. In particular, I can say that a graph is a gamma expander if the square of the Laplacian is always at least gamma times the Laplacian itself in PSD order. I guess the greater than equal to should have been like a PSD greater than equal to. OK, there's a small extra detail, which is such an inequality tells you that every connected component in your graph is expanding. So this maybe allows your graph to be disconnected. But if you start with the mild assumption that your graph is connected, this is an equivalent way of saying that it's expanding. OK, so why study expanders? And it turns out that these objects are connected to various different areas of math, like TCS, also probability theory and stat physics, and also groups. And I think all three of these themes are going to be touched upon in both programs and the workshops. But maybe I will make a slight distinction between expanders in the wild and expander constructions. So for some of these applications, which maybe you should go to QuickWe's talk later in the week, it's about you have some Markov chain that you see in the wild, and you want to say it's an expander because it has conclusions for certain random process converging fast. But in today's talk, we're going to focus on the problem of constructing expanders, that is, engineering expanders so we can use them in various TCS applications like error correcting codes, pseudorandomness, hardness approximation.
Group theorists would say that those are also expanders in the world.
That is fair. So maybe I shouldn't. You shouldn't take this too literally. It's not a translate an opinion. Okay, so now maybe let's try to state the problem that there's a long line of literature that attacks in many ways. So we're going to fix a constant, d, which is at least 3. And the goal is then to obtain an infinite sequence of d regular graphs, maybe one for each choice for the number of vertices, such that each graph in the sequence is a gamma expander. And now you don't want gamma to depend on n, where n is like gn in the sequence. And if you literally just wanted an answer to this question, it turns out that if you take a random d-regular graph, it's actually a near optimal expander with high probability. So it's not hard to show that a random d-regular graph has some expansion, but there's some line of work. Again, you should tune into Jorge's talk later in the week to see why they're near optimal. So okay, let's refine our goal a little bit. Today we will be talking about obtaining explicit expander constructions. So we not only want the sequence to exist, we also want an algorithm that is deterministic and runs in poly-n time that can construct an n-vertex graph, which is a gamma expander. Actually, there's a stronger notion that a lot of the graphs that we will discuss today satisfy, which is that of being strongly explicit, which is we even have like a local poly-log n time algorithm for navigating the graph. That is, if I give you a vertex, v, you can output its list of neighbors in poly-log time. Okay, and over the years, these have been approached via a wide range of different techniques. There's many different constructions, and they truly all look different from each other. And hopefully, over the course of the semester, you'll learn something about each of these paradigms. But again, today, we're going to focus on the first, which is that of an algebraic construction of an expander graph. So without further ado, let me start off by actually literally telling you one simple example. So you can, so even if you stop paying attention after, you can walk out with like the knowledge of one expander in mind. Okay, so here it is. So let me slowly break it down. So you have a group, and maybe you should think of this group as being the vertex set of the graph that you're constructing. So in this case, the group is going to be all 2 by 2 matrices whose determinant is 1, and the entries are in the finite field of size q. Maybe even think of q as being like literally prime. So the entries are 0 through q minus 1 mod q. Okay, and then I'm going to define a 4 regular graph on this particular vertex set. And the way I'm going to define this 4 regular graph is I'm going to literally pick 4 matrices And the 4 matrices are the ones marked with the arrows here, which is ones on the diagonal and then a plus or minus 1 entry off the diagonal. Okay, and then I connect 2 matrices with an edge. If I can take one of those matrices, make a move, where a move is to multiply the matrix with one of these 4 generators on the right. So in this case, actually, multiplication by these matrices has like a fairly intuitive explanation. It's basically a column operation where you take a single column and then you add or subtract it to another column. So this preserves determinants, so you're like actually staying in the group. Okay, so if you have A, B, C, D, then those are going to be your 4 neighbors. But you can imagine as you walk more along the graph, you can get to pretty different looking matrices fast. Okay, so this is a pretty simple to describe expander family. And it has inspired a lot of different ideas. There's actually 3 pretty deep proofs of the fact that this is an expander. The first 2 are based on analytic number theory, and then Bourget and Gambert had some additive combinatorics based machinery. Okay, so we're actually not going to be talking about any of these. I mainly showed you this example sort of as an impetus for showing you like a mildly more complicated example that's a lot easier to analyze. Okay, so you can imagine the same story, except instead of 2 by 2 matrices, you work in the space of 3 by 3 matrices. So again, you have 3 by 3 matrices. They all have determinant 1. Entries are in a finite field FQ. And now, once again, you connect 2 vertices with an edge. If you can do a column operation to go from one matrix to another. By the way, I realized I did not define something. So here, a lot of you may be familiar with it, but let me just define it a bit more precisely. So actually, in general, if I give you a group, and I also give you a subset of group elements S, then the Cayley graph of that group with these group elements S, which I'm calling K of gamma S, is basically a construction akin to what I showed you in the previous slide, which is you connect 2 of these group elements with an edge if you can multiply an element of S with one group element and reach the other. Okay, so anyway, when you define this particular graph over SL3FQ, then you actually naturally get an infinite family of well-regular graphs. And the way you make this infinite family is you can take your prime Q and just amp it up, make it large. Like you can find arbitrarily large primes. And it turns out that there are way more elementary proofs of the expansion of this particular graph. And in some sense, we're going to see the theory of how one proves expansion for a certain family of groups, such as this one. Maybe I'll pause for a second to see if there's questions.
Are any of these optimal?
Are any of these optimal? Good. So neither the previous slide nor this slide are known to be optimal. I think this one, there might even be some impossibility.
This one is not.
This one's not, yeah.
Could you say what optimal means?
Yeah, okay. So I guess the way I interpreted the question of optimal is, like, let's say someone gives you a D and then asks you for a D regular spectral expander. It turns out that you cannot, this second eigenvalue is always larger than 2 square root D minus 1 minus a lower order term in the number of vertices. And I assumed optimal meant you hit normalize, yes. I was working with the normalized.
For P,
For
the transition matrix.
yes, so lambda 2 of PG. Okay, good. Yeah, and I guess in general, the kinds of proofs we know only show some constant gap away from 1 for the transition matrix.
And optimal would be
Right. So optimal would mean the second eigenvalue is at most this quantity. And such graphs are known to exist both via explicit constructions and also random graphs. Okay, so the plan for today is to talk about the so-called theory of easy proofs, which, okay, it's going to be this framework of using some squares to prove expansion. I'm going to explain everything about it, so if those words don't make sense to you, it's fine. Okay, and then I want to give a brief overview of how one actually analyzes the spectral gap for this set of 3x3 matrices. But unfortunately, the OV I'm going to show you is going to result in a computer-assisted proof. So in the last part of my talk, I wanted to also give you a fully self-contained proof for expansion of a related family. So not quite the one in part 2. Okay, so maybe I'll start out by telling you the simplest way in which I know to prove that a graph might be an expander. And I guess it's related to HTXs, which you should tune into Mitali's talk later in the week to see what it is. Okay, so let's say you have a graph. Now I'm going to define a notion of something called a link. Okay, so you choose a vertex, V. I chose some vertex in the center. And then you look at its neighbors. And you look at the induced subgraph on its neighbors. In this case, it's some like 6-cycle thingy. Okay, so terminology here is the link of a vertex is actually the induced subgraph on the neighbors. And why is this an interesting notion? So there's actually something known as the trickle-down theorem that lets you use properties of the link to show that your graph is an expander. So okay, so this was a theorem that actually dates back to Zhuk from 2002. It's also implicitly there in this work on de-randomized squaring by Rosenman and Verdhan. And then there was a higher dimensional generalization proved by Oppenheim in 2018. Okay, so so now I can basically state what the theorem is. Basically, it says that if you have a graph such that every link, that is, for every vertex, I look at the neighbors and look at the new subgraph. If the link is a pretty good expander, that is, if its spectral gap is larger than a half, then it actually lets me conclude that every connected component of the full global graph has some amount of expansion. And you can make this more precisely quantitative too. That is, if the gap is gamma, then the global graph's gap is 2 minus 1 over gamma. And as you can see, half is sort of like a point where this starts to become a non-trivial statement. So if you just knew that your graph is connected, then simply having this local viewpoint from every vertex, that is every link is an expander, is sufficient to imply that the global graph is an expander. So I find this, yeah.
You said that this is Rosenman-Verdhan, but I don't see that because in Rosenman-Verdhan you also need to assume something about the global graph.
Right. Okay, so maybe I can say what the connection is. So Rosenman-Verdhan defined this operation called de-randomized squaring, which is, suppose you take a graph, and if you were to square it, that is, put an edge whenever you see a length 2 walk, then you can actually equivalently think of this operation as taking each vertex and then putting a clique on its neighborhood. The reason is, like, let's say here's a vertex v, and then you have a bunch of neighbors. If you put an edge for every length 2 walk, then every length 2 walk passing through v is going to result in an edge, so you put a clique. And the idea of Rosen and Sidhanth was, okay, first of all, when you square a graph, you improve its expansion, but you also make its degree a bit worse. And the idea of Rosen and Sidhanth was, if you take this clique but sparsify it, that is, instead of placing clique, you place a sparse expander, then you still get the same boost in expansion that squaring gave you, but maybe at not as horrible a trade-off against the degree. Okay, so now one way to actually interpret trickle-down theorem, or the proof of trickle-down theorem, is you actually, if you have a graph whose de-randomized square is itself, so that's the same thing as saying that the link is an expander. That is, if for the sparse expander you use whatever the expanding link is, then what that's saying is this graph is like a fixed point for the de-randomized squaring operation. But de-randomized squaring was supposed to improve the expansion. So if it was bad, it would get better. So it already had to be pretty good to be a fixed point for this de-randomized squaring operation.
I don't see, but I'll ask you.
Oh, okay, yeah. Maybe we can talk about it more offline. Yeah, Jesse.
Do you actually need every graph to be the same, or that's just so you have one gamma?
No, you actually don't need every graph to be the same. All the links can be completely different, and as long as every single link has a spectral gap larger than half, you get this conclusion.
I guess you need some triangle regularity or something, otherwise the weights will be screwed up.
Yes. So okay. So actually, the graph needs to be presented to you as a union of triangles, but I was hoping to not talk about that. or okay, I guess I made the assumption that H is regular. Yeah.
Is the conversion from gamma to 2 minus 1
It is tight. So the examples. Actually, for every gamma, you can construct an example, and the example is actually just a sphere graph.
Wait, the what graph?
Like the sphere, you take the unit sphere and then connect things which are angle at most something. Yeah. Abhishek, did you have a question? Okay. Okay, so you actually don't need all the graphs to be the same, but I wanted to make that assumption. Firstly, because it's true in Cayley graphs, but secondly, it also lets me articulate a proof in a way that generalizes to other settings. Okay, so maybe let's talk about what trickle-down might look like in a Cayley graph. So you have your set of generators, G1 through GD, and every link is the same. Every link is equal to this particular graph H, which has some spectral gap gamma. Okay, so now if I zoom into a single edge in the link, well, because it's an edge, it actually has to exist because they differ by some generator element. And without loss of generality, I can look at the link of the vertex labeled identity. Okay, so this picture is actually saying something. It's saying that if I walk along a generator GI, then walk along F, I reach GJ, and if I walk along GJ inverse, I reach identity. So it gives me a relation of some sort. Okay, so with this relation in mind, I can actually think of the random walk matrix of the graph as being written in two ways. So first, the definition of the random walk matrix is I pick a random generator GI, and I look at the adjacency matrix of that generator. So I guess I am going to conflate and identify group elements with their adjacency matrices. OK, but since an element GI happens to be equal to a product of two other elements, and possibly in many different ways, I actually have this alternate way to write down what the adjacency matrix is. And in particular, I can think of it as picking a random edge, ij, in the link, and then looking at GI inverse times tj. So essentially, the thing that I'm doing here is I'm using the fact that every link edge gives me a relation of this sort. So picking a random generator is the same as picking a random place where that generator occurs in the link and looking at GI star gj.
So this is the adjacency, the random walk operator of the link, not of the graph. It's a d by d matrix, yes?
OK, so PG is an n by n matrix. You should think of it as being the random walk operator of the on the entire global graph. But OK, I guess there is like a little bit of sleight of hand happening here, and I will like try to go slowly and say what I'm actually doing.
Maybe it's good to say, when you said GI is an adjacency matrix, you meant an n by n matrix of the matching.
Yes, correct. So it's like in the Cayley graph, I can attribute each edge to one of the generators. So I can write the random walk matrix of the Cayley graph as an average over the adjacency matrices of individual generators. So maybe I can even try to define it more precisely over here.
So this might be too low for people to see because of the podium.
Oh, I see. Maybe I'll use the other board. So GI, when I think of it as a matrix, I am identifying it as the n by n matrix, where maybe in the f prime entry, I have a 1 if f times gi is equal to f prime. That is, I can use the generator to walk from f to f prime. And it's going to be 0 otherwise.
Sorry, what is n here?
What is the dimension? It's the size of the group. So n is equal to the number of elements in the group.
So it's just a permutation matrix.
So it's just a permutation matrix.
So is there some mean over H too? Like, because there are lots of links, right?
So all of this is happening in a single link, actually.
For any H.
Yeah. So OK, I guess first of all, one thing about the graphs that we're working with is that all the links are the same H. And I'm looking at this from the perspective of a single vertex, which let's say is identity.
I guess I don't see why they equality for between the number I in B and ij in A.
Yeah. Okay. So we can. So it's okay. Maybe it's something that I should like spell out more clearly. And I can try to do that on this board. So okay, let's say you have your vertex V over here, and then each of its neighbors I can identify with the generator. It has D neighbors, so its D neighbors are G1 through GD. And then now, in the neighborhood, there's going to be a few links. So say a few edges. So for example, maybe I have like purple edges which correspond to G1. Then I'm going to have red edges which correspond to, like, say, G2, and so on. Okay, so what you should, yeah.
But this link doesn't have to be regular, for example, right? Because
It does not have to be regular. So
it might be even empty, right? And then the quality.
Parallelogram.
yes, so we are actually making the additional assumption that the link is connected, and there's like some extra sort of regularity in the sense that each edge occurs, or each color occurs the same number of times. And actually, the colors don't occur the same number of times. Then instead of taking a uniformly random edge, you would have to weigh your edges in some way. And then maybe the expansion of this weighted link graph becomes the relevant quantity. But I guess for now, I was trying to not pay too much attention to the weights. Okay, so maybe let me like add an extra step in between the two sides of the equality. So here I have like expectation over I gi. Now what I want to do is I want to first take an expectation over I, but then I want to remember that gi actually shows up in a bunch of places in the link. So I'm going to sample jk from an edge from the link of color I. And okay, so here's like a link of something of color I. Then this element is actually equal to maybe GD inverse times G. Okay, so let's say it's like G3 or something. So this G2 is then equal to GD inverse times G3. And in particular, it's going to look something like this. But then this overall distribution, where I first sample one of the original group elements and then an edge which is of that color, I can write in this way. Okay, and I realized perhaps the equality after, where I wrote a quadratic form, might also pack a lot in it. So now I want you to think of G1 to GD as just being formal variables. And these are formal variables that do not commute with each other. And what that expression is doing is it's basically rewriting this thing as a quadratic form with these formal variables. And for these formal variables, you should think of them as like things into which I can plug in matrices. And actually, the matrices that I will care to plug in are going to be the one that I had written here in earlier, like the permutation matrices which correspond to those particular group elements.
You haven't used that all the links are the same yet. This is just true for any particular link in a K-graph. Well, okay, I guess in the K-graph they are. So
Yeah. So I guess this is in some sense using that they're all the same. Because this is like an equality for like the whole global Cayley graph, but I just used the perspective of one link to.
I'm sorry, I'm still very. What do we assume about the groups? Because a group doesn't have to have any relations of length 3, right? I mean, as Amnon said, the link could be empty. For your first examples,
Yes.
relations of length 3. So
Yeah, so this is, so all this holds only assuming that each GI takes part in some relation of length 3. So yeah, I'm assuming like some expansion of the link. Yeah. Any?
Move on, and we can also comment that in Mitali's lecture, she'll revisit this trickle-down.
Yes. That is true.
This was
So
fast, and we'll get a second chance to hear about it.
yes. Though I guess it would be nice if people weren't lost. But yeah, that's a good point. Okay, so now I want to take this equality that we proved, that you can actually write the random walk matrix of your graph as this formal quadratic form using the links random walk matrix. And I want to just say what this is in the Laplacian world. And it turns out that if I just take this equality and stick a 1 minus in front, then I can actually say that the Laplacian of the global graph is the same as this formal quadratic form, but with the Laplacian of the link. Okay, but now I want to actually use something about the links being expanding. And in some sense, the thing that I want to argue is that if I take the quadratic form of, so this is something that if you've not really worked with the Laplacian before, it might look a bit fast, but you can maybe treat it as an exercise to see something like this, which is your Laplacian having a spectral gap is actually equivalent to saying that when you take the quadratic form with some formal set of variables, maybe you should be thinking of them as being matrices, it's PST at least the spectral gap gamma. The gamma is the same gamma as spectral gap of the link times. Now I take a random pair of vertices, I and j, and I look at gi minus gj adjoint gi minus gj. But if you rearrange this expression, again, like an algebraic manipulation that I haven't fully spelled out, you actually get that this right-hand side is gamma times 1 minus the random walk matrix squared.
Sorry, are you asserting this inequality, or are you saying that that's equivalent to proving a spectral gap?
I guess I'm assuming that the link has a spectral gap, and I'm asserting that the inequality is true when the link has a spectral gap. But I guess I want to write this in like slightly more familiar terminology. So this is actually the same as saying that the Laplacian of the graph G is PST at least gamma, namely the spectral gap of the link, times the Laplacian of the square of G, that is the length 2 walk graph of G. So in some sense, what you should be thinking of this as saying is that the graph G that you started out with is about as expanding as its square. So we know that the square graph actually improves the expansion, but this is saying that you're already as good as whatever the improved expander is. And using this, with some amount of rearrangement, you can actually achieve the conclusion of the trickle-down theorem. And basically, I'm just going to flash what the rearrangement is here, which is you observe that the Laplacian of the square graph you can write in terms of the Laplacian and the square of the Laplacian. And then when you do a little bit of rearrangement, you get that the square of the Laplacian is PSE at least this particular number, 2 minus 1 over gamma, times the Laplacian of G. Okay, so this was meant to be like a sort of quick treatment of the trickle-down theorem, but I'm happy to answer any questions that people might have about it.
So in the end, did you need the link to be connected? Like for the trickle-down to work? Not about
Yeah, so we did need the link to be connected, because in some sense the comparison here, this inequality over here, is basically saying that H is approximated by the complete graph on that particular vertex set. And if it was disconnected, you might get that's approximated by a disjoint union of cliques. Yeah.
Do you take the assumptions that we need to make the graph in order for the trickle-down theorem to hold?
Yeah. So let's go back to this slide. So you have a graph, and then every link you're assuming is not only connected, but is also pretty well expanding. That is, it has spectral gap larger than half.
Okay, we didn't need any other assumptions that whether it's the same?
No, so you don't need all the links to be the same. So, but I just presented the proof that way for, I guess we need some.
Once small assumption is already weak, then that's why I sort of raised my hand and lowered it, because I saw it on this. Right, that it just means, if you want to say that the final graph is an expander, you need it to be connected, right? Because otherwise it just says every connected.
Yeah, exactly. Yeah, I think that's a good point. I guess it's like maybe here's like the analogy I like to make for the trickle-down theorem. So say you're on Earth and you look in every direction and you see there's a horizon. So you know the Earth is curved. So and that it lets you conclude that the Earth is actually not that big, but you don't know that there's another object in the sky called Mars. And I guess maybe those are the other connected components.
So you told us the proof of this 4 Cayley graph, right?
Yes.
But you're stating the theorem for some more general graph.
Yes, correct. Right, and I guess before I get into how this idea generalizes to groups where you don't necessarily have connected links, I maybe just want to show you all a couple of quick applications. So actually, working out the details of these applications are in the exercises. So the first one is actually one where you want to show expansion using a very local proof, like such as trickle-down, in this particular model of random groups that was defined by Gromov and analyzed by Zhuk. So here you should think of having n generators, G1 for Gn. For now, you should just think of them as being formal variables. But then what I do is I add a bunch of relations. And these relations are of length 3. And they're the form like Gi times Dj times Gk is equal to 1. And you should think of the collection of these relations as being random. So just to give you all a picture, before you add any relation, your Cayley graph may look like a tree. But now, when I add one relation, it basically folds one vertex into another. Now add a second relation, and then there's like a similar folding that happens. And now, you can imagine once I add sufficiently many relations, the local link looks pretty connected and possibly expanding. And maybe one thing that's in the exercises is to show that the link looks like a random graph and hence admits like a short proof of expansion. Maybe in similar spirit, another graph which admits a short proof of expansion is one where you start with 7 generators, which I'm calling A0 through A6. But really you should think of it as being 12 generators, which is these 7 generators along with their inverses. And then I add constraints, relations of this very particular form, which is AI plus 1, AI plus 3 is equal to 1. So like the pattern on that heptagon. Okay, and then it turns out that once you do this, it forces your link to look like this very particular bipartite graph, which ends up being some kind of point line incidence graph. And actually, this this is going to be some infinite group, but finite quotients of this group are actually what a lot of you may know under the term of like the 2-dimensional Ramanujan complex. But again, I'm not going to actually spend time analyzing this example.
So the structure of this bipartite graph makes it easy to prove if the link is expanding.
Yeah, so it actually turns out that this bipartite graph has a property that if you square it, you get 2 cliques plus some self loops, and then that thing has like a super explicit spectrum that you can, so you can like compute the whole spectrum. Okay, so now I want to take a step back and sort of put the trickle-down proof in some slightly broader framework. So it turns out that if you take the sequence of inequalities that we had from the trickle-down proof, then it is actually basically saying that if you look at this expression, the square of the Laplacian minus some positive number, this 2 minus 1 over gamma, times the Laplacian. Like the thing that we want to show is PSD in order to conclude expansion. It's basically saying that that expression you can write as a quadratic form with some other PSD matrix, where the PSD matrix is M. Maybe don't read too much into what exactly M looks like or trying to verify it on the spot. And maybe trust me when I say that when you go through the trickle-down theorem proof, you can sort of verify by hand that it is essentially saying that the expression on the left can be written as a quadratic form with a PSD matrix. And since it's a quadratic form with the PSD matrix, actually, no matter what I plug into the group elements, as long as they satisfy the relations of the group, that is, as long as the links, so these relations are saying the link has to look like H. As long as they satisfy those relations, you should get a positive quantity on the right. Did you have a question? Oh, okay. Okay, and perhaps one slightly different way to write the same thing is, okay, so here I took this vector of group elements, which I'm calling G, like the generators. And I'm taking its quadratic form of the PSD matrix, which I can write as sum of a bunch of these rank 1 terms. So that literally tells me that this non-commutative polynomial in the group elements G1 through GD on the left, that is given by like the square of the Laplacian minus constant times the Laplacian, it is actually equal to a sum of terms which are of this form, but has some linear polynomial in G times the adjoint of that same linear polynomial. So in some sense, this is like saying that the thing that the reason this Cayley graph is expanding is because this quantity that I want to show is positive is symbolically positive. It can be written as a sum of squares.
Is this equality also modulo the triangle relation?
So the equalities here are all modulo the triangle relations. Actually, I guess if you didn't have the triangle relations, then you generally shouldn't expect these sorts of equalities to hold. Yes?
Correct way to interpret the equalities in the group algebra of the group. Speak about it.
Yeah, maybe I'll give people a second to digest this.
But these V's that you're getting are literally from taking like a Cholesky decomposition of M?
Yeah. So these V's are going to be like pretty uninterpretable. So I think that's why I like to think of it more in terms of the quadratic form, because usually the matrix M is something you might be able to interpret. But in those linear polynomials are not necessarily.
Interpretation of M?
Right. So
It's like the difference between these two things that you want them to be, you think of them as roughly equal, or when you're saying that the Laplacian approximates its own square?
yeah. So actually, that's exactly the place where M showed up. Maybe you can equivalently think of it as so that was a proof. It had some equalities, and I think it had only one inequality. But it's like that one inequality. If you look at what the slack was, the slack ends up being like a matrix like this, and it turns out to be a PST matrix. So then it actually lets you write that difference as a symbolically positive quantity. Yes, Alon?
Just to remark, in practice, it's enough to check this equality only approximately. It's enough to bound the error of how much this term is far from being positive. There's something
Right,
constant,
right.
that if you check that it's like in interval arithmetic, it's above this constant positive, then in fact you have a symbolic proof mathematically. You don't need to find, like the specific V's are not that interesting at the end of the day. Just the fact that they exist.
I'll maybe wait like 10, 15 more seconds.
What you've written makes sense to consider regardless of the trickle-down theorem.
Correct. So maybe the point of the trickle-down theorem is it's like the simplest example I know where you have that expression is positive for symbolic reasons due to being able to write a sum of squares and modding out the group relations. So okay, maybe this the reason I bring this up might be more clear if I consider the next slide. So now let's again remind ourselves of the setting we've been working with. So you have a group gamma and S is a set of generators. And I'm going to be interested in the Cayley graph, whose Laplacian has that form. Okay, so now this is a group, and a group might have like a ton of different kinds of relations. But let's momentarily restrict our attention only to relations of length at most 2k. So I have like G1 to GL, L is like some number that's at most 2k. If I look at the product G1 to GL, I guess the 2k that should be an L. I end up getting the identity element within the group gamma. Now I'm going to make a definition. And the definition is that the Cayley graph G has a degree 2k, or equivalently radius k, sum squares proof of expansion if the square of the Laplacian minus kappa times the Laplacian, think kappa as being like a small constant larger than 1, larger than 0, actually can be written as a sum of a bunch of polynomials of G times the same adjoint of the same polynomial. So each of these terms here is symbolically PSD. No matter what matrices I plug in, I should see something PSD. But this equality is modulo the group relations. That is, once I expand out the expression on the right, I'm allowed to, whenever I see like some string of group elements that happen to equal identity, I'm happy to just substitute all of them to being identity. Which sort of should make sense because the left-hand side is like only degree 2 in the group elements, but the right-hand side I'm allowing it to be big degree, so okay, the only way this could work is if like cancellations happen due to the relations. Or equivalently, I get to write the expression on the left as some sort of quadratic form, where M is a PSD matrix, and G you should think of as being, or G atmos K, you should think of it as being all words of length atmos K that I can write down using symbols in G. Now the nice thing about this is it's automatizable. It turns out you can actually write down a semi-definite program to find this particular matrix M. So now let's say tomorrow you encounter a group and someone gives you some generators and you're like, well, okay, like is this group expanding? Maybe you could try to do something deep with it, but perhaps the first check is if it's expanding for the simple reason that it has a low degree sum squares proof expansion, then you could check that using a semi-definite program. Yes, Noah?
But sorry, like an even easier thing you could do is look at the link and check whether it's an expander, right?
That's an even easier thing you can do.
But this is more, you're saying...
And this is a more general framework. So basically, the point is link expansion is like a radius 1 proof, or equivalently a degree 2 proof. Did you have a question? Okay.
Can you explain again the expression with the G less than equal to K? That's like all the K tuples of elements in G?
Yes. I guess
So then M would
all
be-
products of K.
Right, so I mean, order.
And ordered, yeah.
Right, and so M would be a much like an n to the K by n to the K?
Yeah, so in that case, M would be an n to the K by n to the K matrix.
But you don't have a bound on K a priori, like given a group. You don't know.
So yeah, exactly. Like actually, in general, if you have a finite group, then you know that you can always find an SOS proof of degree atmos the size of the group. But if you have an infinite group, then you have no guarantee that there's going to be a finite degree sum squares proof. Yes.
What does it mean G smaller or equal to K?
Wait, say one more time.
What does it mean the G smaller or equal to K?
Yeah, okay. Let me actually just write that out over here. It's equal to or equivalently, like I take all words of length atmos K. So it's just going to be some vector of words in G. Yeah.
This SDP doesn't like require solving the word problem or anything? Or the...
It does not require solving the word problem.
Okay.
Because you're just taking some fixed set of generators and you're checking whether there's like a sum squares proof of this thing being positive.
This last equation that you wrote, that's also modular relation.
Yes. So yeah, sorry, all equalities here are going to be modulo the relations.
Can you check? You can efficiently check whether two things are the same modulo the relations always?
So I'm not sure of the exact complexity, but like let's say you have a list of relations, and you can probably do it in like some time which only depends on K, and here in K is being like constant, then
In general, it's undecidable.
in general it's undecidable. Okay. Oh, okay. So maybe not, but hopefully for things like SL and such,
Yeah, I guess if they're actual matrices, you can just check the.
Yeah.
Yeah.
Yeah. Okay, so actually this says something stronger. Like, in particular, you don't actually need the graph to be a Cayley graph, as long as you have some connected graph, and then you color the edges in some way. Like, you color the edges using the generators of the group. Suppose every radius k neighborhood happens to agree with whatever the Cayley graph of the group is, which might be some infinite object. You actually get that this particular connected colored graph is going to be an expander. Because, again, I want to emphasize that equality there is basically like a symbolic equality, assuming that these relations hold. So if I plug in any matrices which satisfy all the relations up to length k, and it need not be a group because it need not satisfy relations of length longer than k, then you do get expansion for that particular graph. Okay, and maybe the last thing I want to mention is a lot of things that I described in this talk. It's maybe not actually quite the historical order in which things happened. It's definitely like a little bit of a revisionist history. So these so-called easy proofs, actually, they first studied by Kashdan in '65, and you may have heard it under the name property T, which is some property of the group. I think Alon is going to get into it more in the next talk. And it was proved by Ozawa in 2013 that having that particular property is equivalent to having these low-degree sum squares proofs of expansion. So at least I like to, I guess I'm more familiar with the latter object, which might be my bias, and hence this particular presentation. But you should see the equivalence between property T and SOS proofs of expansion in the next talk. Okay, so now I want to go back to this particular example that I had promised I would say something about, like this 12 regular graph over SL3. Because unlike the previous examples I showed you, like the random group example, we know it's an infinite group, we don't know finite quotients. I guess for the second example, getting finite quotients is more non-trivial, but here the finite quotients are actually readily available. So I want to say something about how you prove that this particular Cayley graph, which let me remind you, it's like 3x3 matrices, determinant 1, entries in FQ, with column operations as being the generators. This is actually a family of expanders. And amazingly, the best bounds that we know on the spectral gap are actually obtained by solving a semi-definite program. So you literally set up the semi-definite program from a few slides ago and solve it on a computer. It's some like dimension 121 by 121 program, and that'll tell you that the expansion is like 0.21618 or so. And then if you like amp up the degree, you say, okay, I'm not only going to confine myself to radius 2 relations, but I'll also allow radius 3 relations, which like things are degree 6. Okay, then you get something that's maybe of dimension close to 1000 by 1000, and it has expansion that's a bit better. So okay, so this is nice in the sense you don't actually need to do anything deep to prove that these graphs are an expander. You just set it up the right way, and then like a very mechanical algorithm can check that these graphs are expanders.
The point is you only need to do it once for the infinite graph. You get it from.
Yes. So if you do it once for these relations, like basically same relations are satisfied for like every Q.
In this graph, the links are not expanders?
the links are not expanders. In fact, I think there might be a theorem that says that no matter what set of generators you take on SL3Z, the link always has expansion worse than half.
What happens if you try radius 4 and so on?
Right, so it's conceivable it gets better, but I think the semi-definite program gets like intractably large or you might need to run it for months or something.
3 months for the program.
I mean, it's not literally true that these all have the same relations, right? Because like the Q1 has the relation that any matrix to the qth power is the identity. But
no, all relations of length at most like 6 or something.
At most are constant.
Yeah. And maybe think of Q as being like growing. So I'm not gonna like say something like Q equals 5.
Okay.
Yeah. No, so that's correct. They don't have all the same relations. Otherwise, they'd be the same group. But it's instead.
Extra relations are not a problem as long as you have the set of relations for which the symbolic thing is true. Then you're fine.
But what is the actual set of relations which you? Just for SL3Z.
So it's the one set hold for SL3Z. Yeah. Yeah, good question. Okay, so maybe in conclusion for this part of the talk, if you can actually in the formal group algebra, express the square of the Laplacian minus kappa times the Laplacian as this quadratic form with a PSD matrix, then it automatically for free tells you that if you take that expression, plug in any set of unitaries satisfying the same relations, you get that the spectrum of whatever Laplacian you have is like it either has eigenvalues at 0 or bounded away from 0 by some amount kappa. Okay, so I guess I have like 20 minutes left, and I could take a few questions. And on the board, I wanted to show something, but maybe that's like of secondary importance. So I'll take questions first.
You have time? I mean, otherwise you can go back to the place where we got a bit confused.
To which one?
I mean, when you started doing the trickle down,
Mm-hmm.
I think we got a bit confused, and if you have time, maybe we can revisit that again. I don't know.
Sure. I think that seems good. I guess I saw a few hands, so I can like first. Yeah.
So eventually, when the decreased eigenvector net will become approximately eigenvectors of L. The question about the group algebra.
Oh, wait. So yeah, yes. The question is, what are the eigenvectors of L?
It will eventually approximate the eigenvectors of L. Is the
Yeah, that. Oh, the right-hand side. Well, okay. I guess that's maybe not so clear because. Yeah, I'm not sure whether you get the eigenvectors of L.
Because I guess it's an algebra with the left-hand side. It's just like a polynomial.
Oh, I see. You're saying once you make the degree k like super huge, then what is it you get?
That's what it is.
Well, if it's an infinite group, it might not have eigenvectors.
Yeah.
Example that you are about to show on the board, does that use the trickle-down theorem, or?
No, so it's actually not using trickle-down theorem.
So you have a basic example of a graph of an expander that we get as a Cayley graph using the trickle-down theorem?
Yeah. So I guess maybe this is the simplest example. So as presented here, it's actually an infinite group. Maybe for the infinite one, the random one might be easier, but I like this one because you can also get finite quotients of this. I guess the finite quotient Cayley graphs are a little bit harder to describe what exactly they are. But yeah, so this is actually one of the exercises, so maybe I won't actually work it out right now.
Could you say a bit more about how the trickle-down theorem is related to the sum of squares proofs that you found using an STP?
Yeah, so actually, the trickle-down theorem proof, you can interpret it as being a radius 1 or degree 2 sum of squares proof. And in particular, okay, so maybe we can like go back and see what happened in the proof of trickle-down. So over here, there was like some inequality that took place, but maybe you could think of this inequality here as being like an equality, but I have this term, but then I have like some term that looks like the difference of the right-hand side and the left-hand side, which happens to be like a square term. So it turns out that whenever I write an inequality here, the inequality is true because, or okay, for example, here the left-hand side is bigger than the right-hand side because I can obtain the left from the right by subtracting a square term. Yes.
So is it known whether the infinite group, the triangular group, have property?
It is known. And in fact, you can prove it with trickle-down. I guess for some range of parameters. Yeah.
So, okay, I'm trying to make sense of this slide. So, in this slide, you tried to prove the trickle-down theorem in a special case where we're talking about a Cayley graph. And let's even assume it's very regular, so that for every generator Gi, there is the same number of Jk such that Gi equals Gj times Gk, or something like that?
Yes.
Let's pretend that.
Yeah.
Then okay, so you wrote Pg equals expectation Gi. That's just, Gi is a matching, and you just take the average over these matching. Then what's the second equality?
Yeah, okay, so let me like spell this out. Maybe it was like so similar to a question that Abhishek asked before. So I'm going to break that equality into two equalities to like clarify what's going on. So first I have like expectation IGI. But now maybe let me think of it as being expectation I. And then I'm like, here I'm going to put like something of color I. But what I'm going to do is I'm going to look in the link. And in the link, I'm going to ask, where did I see color I edges? And
generators are a subgroup. Maybe this is like really easy to see.
If the generators are a subgroup, it's really easy to see.
No, but then
I don't know if that's
yeah,
like
yeah,
a,
I know.
It's a disconnected graph.
Yeah, so now maybe I want to sample an edge jk in H, but I'm going to condition on gj, gk inverse being equal to gi. So it's like every edge in the link has some color, but what I'm doing is I'm first fixing a color, and I'm picking a random edge of that color. Okay, but then, so this is just like the same expression. I just like broke down the expectation. But now let me plug in gi equals gj times gk inverse.
Sorry, are we in a single link or
So this you should think of as happening in like across all links, but it suffices to consider, like, let's say only the identity link to see that these relations are true. I guess here I'm writing like some statement that's true for the group.
So I was just saying that if it's a subgroup, then like the ratio of two generators is always another. Okay, of course it's disconnected, but.
Oh, I see. So then you're saying for the subgroup, then like I can just take J and K even independently.
Yeah, like you want to. You want to be really lucky that you have a sparse set of generators and it's still connected, but that ratios of two generators are again a generator.
Correct. Right, and okay, I do know that there was some confusion around like, does each color need to be represented the same number of times and so on. So I guess if you write it this way, each color just needs to be represented at least once, but then you don't necessarily get the uniform distribution over edges. And maybe if you want, and then you get some like weird weighted link, and then it's like the eigenvalues of that are going to be relevant.
The reason this doesn't apply to SL3Z is that the links are empty, or they're not empty?
Yeah, so in SL3Z, actually, okay, at least for the row column operations, the links might even be empty. I guess there is also something about how in SL3Z, no matter what generators you pick, your link will always be like expansion worse than half.
Why?
Actually, don't know what the proof is. Actually, okay, maybe let's also take that with a grain of salt. Like I learned this back by like querying an AI, but didn't like look at like the source. So I'll report back after I look into it more.
So you're going to tell us one example where you can use trickle down to produce SOS?
Oh no, I guess this example was using not trickle down. Oh, so maybe the random triangular groups and.
But I meant part 3 of your talk.
Yeah, so part 3 is a non-trickle down SOS proof.
The simplest one, the KO.
Okay. So the KO complex is definitely like the simplest example of a link. Right. But is that a Cayley graph?
No, but it's still trickle down.
Yes. No, I guess I was hoping to maybe like the point of this example is also to kind of show that there are examples beyond trickle down for when like you can have an SOS proof of expansion.
Here you can actually do a trickle down in that example.
Oh, you can do trickle down for this?
Yes.
Oh, okay, I wasn't aware. But presumably with like a different set of generators?
You will take a different set of generators and you can do it.
I
The
see.
property T preserves across sets of generators. So if you prove property T for one set of generators, you get property T for your set of generators. So
Right. Yeah. No, I guess maybe. Yeah, I should also like emphasize this particular fact a bit more, which is if I give you two distinct sets of so this is also one of the exercise. If I give you two distinct sets of generators, then and you show like an SOS proof expansion for one of them, then you actually also get one for the other set of generators for free, like via some like powering type argument. But okay, maybe in the 7 minutes that I have left, I will attempt to show you some proof of expansion for this particular group. So it's not quite SL3F for Q being prime. Instead, it's a prime to the K. And okay, I picked 5 just sort of arbitrarily. You only need the prime there to be bigger than 5. But it is kind of important that you're in a prime power, because we are going to use the fact that F prime power is actually like polynomials, but then you mod binary reducible in some way. Okay, so maybe let me give these generators names. So I'm going to use A to denote like identity plus minus E12. B is identity plus minus E23, and then C is the final one, which is identity plus minus this variable x times x31.
Plus minus mean 2 elements or 1 element?
They're 2 elements, so maybe let me call this like A plus minus B plus minus and C plus minus. So I have like 6 generators. Okay, and now the thing that I'm interested in is like identity minus 1/6 times so actually the first thing that, okay, so I actually don't know how productive it is to try to cover this, because the proof does involve like a few like slightly non-trivial steps. So maybe I can instead of like focusing on this example, I can tell you all like some slightly general principle that you can extract out of this. Okay, so let's say you have a Cayley graph gamma, and the generating set is actually the union of 3, it's a disjoint union of 3 subgroups. So G1, G2, G3 are okay, so now the local view of a vertex looks like the following. So here I have a vertex V. Let me use three different colors to draw what's happening. So maybe here I have like all the edges which come from the first group G1. And then in red, I have the edges that come from the second group, let's call G2. And then in black, I'm going to have edges coming from the third group, let's call it G3. Okay, so now I'm going to define 3 types of links. There's going to be the purple-red link, the red-black link, and the black-purple link. But okay, it's not what it seems like. It's not going to be like the union of the black set and the purple set. It's instead going to be, so maybe let's focus on the purple-black case. It's instead going to be the, so I'm going to define a subgroup like G13, and it's going to be the subgroup generated by G1 and G3. So in particular, like each vertex here has its own purple subgroup coming out, and then each purple vertex has its own black subgroup coming out. But now it's possible that like these overlap in some way. Okay, so here's the theorem. It says that suppose each of these new links, that is the Cayley graph of, say, G13, but with G1 and G3 as being generator sets, have a spectral gap bigger than 1/4, then actually this overall original graph, G, is expanding. Okay, as long as G is connected. And I guess that was, that's sort of the principle that you can apply here. So now it's no longer just, at least this proof is no longer just trickle down on like one set of generators, but is instead some like generalized version of trickle down where you have like 3 different kinds of links, and then you check all of them have a gap bigger than 1/4. And the links in these cases end up being like nice algebraic objects, like something known as the Heisenberg group, if you've heard of that. But okay, I think at this point I'm out of time.
Okay, thank you so much. I have time for a question or two, if people want to ask.
So in this example, what's the degree of the SLS certificate?
Oh yeah, so in this example it actually ends up being like kind of big, I think like 125 or something. Or at least with like some loose accounting.
It's something you couldn't search for in a computer in particular.
Yeah. Though that might just be me being silly, but it's possible there's like something more you can do.
All right, thank you again, and we'll reconvene at 11.